Hey everyone, welcome to the channel. In today's video, we are going to solve a common optimization problem called the Traveling Salesman Problem using Julia. I will show you how we can use an algorithm called Simulated Annealing to find a good solution. We will walk through the code step by step, run it multiple times, and at the end, we will find the shortest route. And if you are new to this, don't worry, I will explain everything as we go. And let's start with the TSP, I mean the Traveling Salesman Problem. It is simple to understand, and let's consider you are a salesperson who needs to visit a set of cities, and you want to find the shortest possible route that visits each city once and returns to the starting point. And here, the challenge is to find the best route when there are many cities. This problem gets harder the more cities adding. We add. And we will use an algorithm called Simulated Annealing to help find a good route. It is not guaranteed to be perfect, but it's a good way to get close to the best answer. And Simulated Annealing is a method that helps us find good solutions by randomly exploring different routes. And the idea is that we start with a random route and then slowly improve it by swapping cities in the route. As we go, the algorithm decides if we should keep the new route or stick with the old one. Over time, it gets better at picking shorter routes. And uh, let's walk through the code and I will show you every part. So here using random and using print, what are these? Sorry, these two lines are importing packages that we need for the rest of the code. And random is used to shuffle the cities or generate random numbers like for the random coordinates of cities. And printf, what is it? It is used to print results in a formatted way, which makes it easier to display things like number of with a specific number of decimal places. And this line const num cities equal 20. What is it? We are setting a constant value for the number of cities in our problem, and here it is set to 20. This means we are solving the problem for 20 cities. So next line here quotes, I mean coordination, and rank 2 for in here 1 and num cities. What happens here? This line, let me select this line creates a list of random two-dimensional coordinates for each of the 20 cities, and rand 2 here it generates a random pair of numbers and which are the x and y coordinates for each city, and we do this for each city from 1 to 20. And let's switch to function. Let me select like that. Here we have a function here, and this function calculates the straight line distance and between two cities P1, as you can see here, and P2 here. Inside the function we are using the distance formula. You can see squares, and here P11, P21 is they are the x and y coordinates of the first city, and P21 and P22 are the x and y coordinates of the second city, and it returns this calculated distance. And let's look at the total distance, and let me select and let's switch slightly. Okay, what happens here? Let's talk again. Function total distance, and tour. What is it? This function calculates the total distance of a given tour, which is a sequence of cities, and the tour, here, is an ordered list of city indices. So, what is dist equal 0? We start by setting this to 0, and this variable will hold the total distance of the tour as we calculate it step by step. And here, for loop for I in 1 and length tour and -1. What is it? This loop goes through each pair of consecutive cities in the tour, and tour I, for example, you can see here, represent the current city, and tour I plus 1 represents the next city, and the loop runs from the first city to the second to last city. And inside the loop, we add the distance between tour I and tour I plus 1 using the Euclidean distance function we defined earlier. You know that here, Euclidean distance. And the distance here between each consecutive pair of cities is calculated and added to dist. Here, dist started with 0. You know that. And after the loop, we add the distance from the last city back to the first city. And this ensures that the tour is a complete loop, which is important for problems like the Traveling Salesman Problem. And return dist here. Finally, the function returns to the total distance of the tour, which is stored in dist. Dist is important. So, let me switch to another function, and here we have a function again, and name is initial tour. What happens here? This function creates a random sequence of cities to represent the initial tour, and what is it? Return, let me select like that, return shuffle and num cities. What is it? It generates a list of city indices from 1 to the number of cities, and shuffle here you can see it is randomly shuffles these city indices, giving us a random tour of all the cities. And this shuffled list is the starting point for our simulated annealing process. And I hope it's okay. And next function is swap underscore cities and tour. So what is it? The purpose here, function swaps to two random cities in the given tour to create a new tour, and I j equals sort random, rand, and it is num cities 2. And what is it? Especially this sort, this part, it picks two random city indices, and sort arranges these indices in order so that I is always then smaller than j, and this prevents accidental swapping of the same city. It is important. So how about the new tour? Here new underscore tour and equal copy tour. What is it? This creates a copy of the current tour so that we don't modify the original one. And here new tour I, new tour j equal again new tour j and new tour I. What is it? This swaps the two cities at positions I and j in the tour, and it returns the new tour with the two cities swapped. And let's look at another function, and I think we can say it is main function. And here let me select like that, simulated annealing. So let's look at this part, and here current tour and initial tour. The algorithm starts by generating a random initial tour using the initial tour function, and this is the first route or sequence of cities that will be evaluated. And current distance, and what is it? What happens here? Here, after generating the tour, the algorithm calculates the total distance of this route using the total distance function. And this gives us a starting point to compare future routes. And best tour and best distance, what are they? Here we initialize two variables to keep track of the best tour and best distance found during the entire process. At the start, the current tour is also considered the best tour since we have not evaluated any other routes yet. So T and alpha, what are they? T first is the initial temperature of the system. It controls how likely we are to accept worse solutions as we explore different routes. And alpha is the cooling rate, which controls how quickly the temperature decreases. A lower temperature means the algorithm is less likely to accept worse solutions, so the process becomes more selective over time. And let's look at the main loop in the simulated annealing. And while t and this part, what happens here? This loop will continue running until the temperature T drops below a certain small threshold. And here is the value, which is effectively cools down the system. The loop performs the key steps of the simulated annealing process. And new tour here. In each iteration, we generate a new tour by swapping two random states in the current tour. This helps explore the new possible routes that might be better than the current one. And new distance here. After generating the new tour, we calculate the total distance of the new route using the total distance function, and this gives us a new distance to compare with the current route's distance. And what happens here? We calculate this part, and this is the change in the distance between the new tour and the current tour. And if the change, the distance between is negative, it means the new tour is shorter and it is better than the current one. And if it's positive, the new tour is longer and it is worse. So let's look at the if part and acceptance criteria and what happens here. Let's look at this parts first. Here, the new tour is better than the current one, so we always accept the new tour. And otherwise, the new tour is worse, but we may still accept it with a probability based on the temperature T, and this is calculated using the formula and exp and here. And I hope that part is okay. And as T gets smaller, this probability decreases, so the algorithm becomes less likely to accept worse solutions over time. And this randomness helps the algorithm escape local optima and explore different parts of the solution space. And current tour and current distance in this part, let me select these two. If the new tour is accepted, we update the current tour and current distance to the new values. And we have a checking part with these lines. What happens here? We check if the new tour is the best tour. Here. After updating the current tour, we check if the new route is the best route we have found so far. And if it is, we update the best tour and best distance with the new values. And what is it? cooling the system part here. After each iteration, the temperature T is reduced by multiplying it by the cooling rate alpha, and it is less than 1. This is called cooling the system. As the temperature drops, the algorithm becomes more selective, meaning it's less likely to accept worse solutions and return best tour and best distance. Once the temperature drops below the threshold, the algorithm returns the best tour and best distance it has found throughout the process. And for log these returns or outputs, we have a function here. And what happens here? Let me select 66. Okay. This function runs the simulated annealing algorithm multiple times and logs the results of each run. And here num underscore runs and int. What is it? It means that the input should be an integer representing how many times the algorithm should be run, and in this case 20 times. And shortest distance inf. What is it? Testing. It is, shortest distance is initialized to inf, and it is infinity. This ensures that any distance found during the first run will be shorter than this starting value. We will update this variable with the shortest distance found after each run. And best tour overall here, it is initialized as an empty list. Why? This variable will store the best route found across all runs, and it will be updated whenever a shorter tour is found. And we have a loop, and it is main loop. And let's look at for I in 1 and num runs. What is it? This for loop runs the simulated annealing algorithm for the specified number of times, and the loop counter I tracks the current run. And best tour and best distance equals simulated annealing. On each iteration, the simulated annealing algorithm is run by calling the simulated annealing function, and the result is stored in best tour and the best distance, and I hope it's okay. So what is it? At printf and this part. Well, what is it? First, printf is used to print the result of each run in a formatted way, and run, and here this part, it prints the current run number, and it is I. Here I. And let's look at the best tour with %s. What is it? It prints the best tour found in the current run as a string. It's important. And the distance and percent dot 2f, and what is it with that? It prints the best distance with 2 decimal places, and join best tour and sorry, let me select like that. Okay, this joins the cities in the best tour with arrows, and here you can see arrow, and to show the route clearly. And this line prints out a summary of each run, including the best tour and the distance. And check if this is the shortest distance found so far with this if and part. What happens here? And let me select 76 here. So after each run here, the algorithm checks if the current best distance is shorter than the shortest distance found so far. If it is shorter, the current run's result becomes the near shortest distance and the best tour overall. And shortest distance and best tour overall here, next two lines, after 76. And here, if the shorter distance is found, shortest underscore distance is updated to best underscore distance, which is the new shortest distance. And the overall part here, best overall is updated with a copy of the current base storing the new base route. And end part, this marks the end of the for loop, which runs 20 times. And here again, print parts, you can see print ln. What is it? It prints a message to the console, and here it adds a new line before the message to make the output cleaner, and num_runs with $sign. What's it? It is used to insert the value of num_runs, and it is the number of times the simulated annealing algorithm was run. And in this case, it would print something like after 20 runs. And here printf is used to format the output, and here we have sentence shortest distance found, and here %.2f, and here this prints the shortest distance with 2 decimal places, and this formats the floating point number to 2 decimal places, ensuring the distance is shown clearly. And shortest distance here is a variable that stores the best distance found after running the algorithm multiple times. And this part again, best store overall, and here this covers the list of city indices in best store overall to a string with each city separated by an arrow, and here, and log simulated annealing runs. Here the design calls the log simulated annealing runs function, running the simulated annealing algorithm 20 times. This function will run the algorithm, log the results of each run, and then print the shortest distance and the corresponding best store found. And if you are ready, let's look at our output. And I run it before the video for you, and it's better like that. Okay, let's look at the output. What happens here? First, best store found, and some numbers here. This line, the best route found by the simulated annealing algorithm after running it, and the tour starts at city 11, then visits cities 3 and 12, and so on, in the order shown until it completes the loop and returns to the starting point. And each city is visited exactly once before returning to the first city. And total distance 3 points or dots 59. The total distance it is, and this is the shortest distance found after the algorithm was run multiple times, and this value represents the sum of all the distances between consecutive cities in the best route. So to interpret this, the simulated annealing algorithm was successful in finding a good solution to the Traveling Salesman Problem, and the base route discovered has a total distance of 3.59, which might not be the absolute optimal solution, but it is the best one during the multiple runs of the algorithm. So that's all for our video or lesson, whatever you say. And we saw and have learned the simulated annealing algorithm, and we use Julia, and we solve the traveling salesman problem. And thank you for your listening, and goodbye.